It's with great pleasure that I'm introducing you to Charlie Becker, who's an associate research scientist in the MILES group at NSF NCAR. MILES stands for Machine Integration and Learning for Earth Systems. And you may know NCAR is the National Center for Atmospheric Research, and MILES is up there as well. Charlie's here to talk about physical explainable AI, going beyond traditional explainable AI methods in Earth systems science. So without further ado, put your hands together for Charlie and take it away, Charlie.
Wonderful. Good afternoon, everybody. Thanks so much for coming. Thanks for coming to the last session of the day, making it through the day. So I appreciate the introduction. I kind of want to talk about what physical XAI means to me, really from the perspective of Earth system scientists, and really kind of contrasting this with some of the traditional XAI methods that or algorithms that some people may be familiar with. So I'd like to start off with this idea, Clever Hans. I suspect some folks in here are probably pretty familiar with this paradigm. For those that don't or need a reminder, Clever Hans was the name of a horse, and it's a picture of him and his trainer in 1903 in Germany. And the horse could supposedly solve a bunch of intellectual problems, including some basic arithmetic. Could answer such questions such as if the 8th day of the month comes on a Tuesday, what's the date of the following Friday? And Hans would answer by tapping his hoof 11 times. It was years later, after they went on tour and kind of intrigued a bunch of different scientists from a variety of domains, that it was discovered that he had really just learned the simple body language, or I shouldn't say simple, but the hidden body language from his trainer that was unknown to the trainer himself. And I think that's a really important part, right? That it was unknown to the trainer himself, right? And this is such a good paradigm to really describe what happens in machine learning from an explainability standpoint, right? And this phenomenon can really, I think, appear in a variety of different ways, perhaps as overfitting, maybe, although I think in overfitting we have pretty easy ways to diagnose that through machine learning. And so I would say that that's not necessarily unknown to the trainer. But in other ways, the machine learning methods can really learn different relationships than we would expect or maybe want them to, right? And in the worst case scenario, this might be that the machine is learning some arbitrary, irrelevant pattern of the data that we don't care about, right? In the best case scenarios, maybe it's actually performing some scientific discovery. Maybe it's actually learning some physical, things that we don't actually know about in the system, right? That we can kind of extract information from. So I think this is a very useful kind of paradigm to frame this talk. Keeping with the history of some of the XAI development, the medical community, specifically the medical imaging community, was a big leading driver in XAI development. They, of course, have a lot of ethical concerns when trying to kind of bridge this gap between human observation and AI when it comes to medical diagnosis. So in the imaging field specifically, they were a big driver to kind of drive these algorithms to kind of help these attribution methods say, like, all right, what is the AI actually learning? Can you point to what it's seeing to show me what it's learned, right? And this, of course, helps create accountability, transparency throughout the model, and then ultimately build, hopefully, more trust in the human, AI, and ML collaboration. That said, I don't think that a lot of these particular models are necessarily well suited for Earth system science. Of course, there's a bazillion different kinds of models and problems, and some of them might be suited okay, but I think a lot of them aren't. If we're just talking about a lot of these methods that are kind of based for image-based classification, there's some issues when it comes to the different types of Earth system models when we go to apply them. And it's really common to apply these, but I think we need to be really careful about what they're actually representing. So here's probably a non-exhaustive list of some of the problems that I see with XAI and the Earth systems. We use a lot of autoregressive models, particularly of the full state of the atmosphere or some other component in Earth system science. On the diagram there, you kind of see that even in both numerical weather prediction and an AI weather prediction, really we're kind of creating, so I guess in the NWP situation, right, we start with some initial condition, we solve some grid scale dynamics, then we look at the subgrid, maybe parameterize it, solve some physics there, maybe do a conservation correction, and then loop back in and kind of iterate forward in time, right? AI is doing the exact same thing, except instead of actually solving physics equations, we hopefully learn that from training data, and then we encode it, decode it back, maybe make some physics corrections, and feed it back into the model. So essentially, we're taking predictions and feeding them back into the model frequently and rolling them out for a long period of time. This becomes very hard to track, what the model has actually learned through some of these simple methods traditional methods, shall I say. Another major problem is autocorrelated features. Autocorrelated features, all sorts of XAI methods struggle, and it's kind of known and well documented that they can struggle with correlated features. Essentially, different ML models can really latch on to, if you train the same model over the same data multiple times over, it might give you different feature importance for different correlated variables, exactly, because it has no way to separate them, and so the interpretation of that becomes, questionable at best, in my opinion. And we have models that are autocorrelated in all sorts of, all over the place, right? We're speaking as an atmospheric scientist, we're correlated in space in the horizontal, we're correlated vertically as represented by these kind of vertical diagrams here, we're autocorrelated in time, and we're even autocorrelated amongst different variables in the atmosphere, right? So dealing with all of this is a huge challenge in the XAI domain. Long-range and time-lag responses, right? Here's another example. El Nino or La Nina, for example, oftentimes can persist for some given amount of time, but we might not see the effects and different effects over the course of weeks or even multiple years later in the future, right? It becomes really hard to attribute kind of what the model's learned in that sense, right? Especially when we think about it in this autoregressive time frame. There is a little bit of work I think that could be, that has been shown with some of the recurrent neural networks. If you look at the cell state or something like that of a recurrent neural network, you might be able to capture some of that. But a lot of times with these autoregressive networks, that's just not possible. Physicality is rarely preserved through XAI. So a lot of these XAI kind of traditional methods rely on some form of perturbation, right? Where we kind of perturb a feature or a set of features, see how the model responds, and perform some analysis or composite on that to kind of demonstrate here's the sensitivity of maybe a particular feature or something like that. It's a really common, there's a variety of methods that use an approach like this. But it's very easy to break physical laws if you're taking an independent feature, especially when they're so correlated like we do, and we start to perturb them throughout some space. All of a sudden your physicality is not there anymore, right? And the XAI doesn't know anything about that. It's still going to give you a result. And so I think our interpretation of the XAI at that point becomes, again, really, really questionable, right? If we're kind of like out of domain, out of sample, essentially, in these regimes that don't exist in real life, what's the XAI really telling us? And lastly, computational expense. With the huge data sets and all these different methods, especially if we're trying to kind of see feature interaction amongst different features, it becomes extremely expensive, which is a problem in itself. So I'd like to kind of talk about, this idea of physical XAI, what it means to me. And what it means to me is that it should be a process, right? An end-to-end process. And I don't feel it should be constrained to an algorithm, right? Like when I hear the term XAI, I feel like it really is just talking about some algorithm that we should apply to some trained model or something like that. And I'd like to get away from that, that thought process, and think of XAI from a scientific standpoint that we're domain experts, or, they can look at the data. There's so many kind of creative ways that we can either take traditional methods or deal with the data coming out of the model or the input data to kind of preserve some of the physicality, or at the very least inspect it and kind of curate our data so it kind of obeys some of this stuff. So the first question, right, is the training data physically consistent in itself, right? There's all sorts of examples where this doesn't happen. I'll show you one in the next slide or so. What happens if a frog jumps in a rain bucket during a big rainstorm, right? Or a windstorm knocks over a sensor, or a bird builds a nest in a sensor. Like this stuff happens all the time where we get really bad observations, right? And we train models on these data all the time, right? Like to think that our data is bias free and free of errors, and that good quality control is being performed on our data on a regular basis is in my opinion, just like naive, right? Like we need to kind of perform some careful data curation to kind of make sure that it's physically consistent, right? Physically or feature selection and or engineering can also help, especially if interpretability or explainability is extra important. This can, of course, vary based on how much you care. There might be some trade-offs. Maybe it's worth trading off a little bit of accuracy in your model if it's far more interpretable, right? And so if you can kind of feature engineer some features that are less correlated to get some more interpretability out of it at the cost of a little bit of accuracy, maybe it's worth it. Next is the model output itself physically consistent, right? And this is where we need to really involve domain experts, right? What's a classic example in ours? Like, what if we train an ML model and it predicts a small amount of negative rain, right? Like, and this happens. Like this definitely happens, right? It's a small amount. Maybe we can just say, okay, well, let's just clip those at 0, right? Like, let's just anything that's negative, let's just clip it. Is that going to be a satisfying answer to a physical-based scientist that's been building physical laws? Like, probably not. So is there a way to explain why an ML model would predict a negative amount of rain? So I think we need to involve these domain experts. We need to do local case study and regime-based analysis, either with the XAI itself or kind of interactively with the model development and in an interactive way, which I'll show in a little bit to see kind of what the failure modes are and how the model responds essentially. Do the traditional XAI methods render something useful? Can we modify them in a physically meaningful way? I talked about kind of perturbing one feature at a time and kind of violating that physical space. Are there some smarter ways that we can go about doing that actually preserve the physicality and give us a better interpretation? Do we have the right tools for the job? I think that in some cases we do, and in some cases we don't. I think that what can we learn from other domains? I can say in this conference alone in the last 2.5 days, I've seen a ton of tools that are really common in other domains, bioimaging specifically, and I'll demo something like that, that can really be readily applied to the data that we have directly. Another one is if anyone's familiar with global sensitivity analysis, right? This is the suite of kind of algorithms and tools that are applied to physical-based models that are meant to kind of sample sparsely. It's a variance-based method that's actually meant to test the sensitivity of different, tunable parameters, in a model, but not an ML model specifically, right? And they call them the sensitivity analysis. Like all that is XAI just for a non-ML method. We can use these methods for AI from a different domain, and they actually have some advantages. I don't have time to talk about the details of that, but they actually have advantages of being able to kind of capture interfeature interaction, which is important in these nonlinear systems. Okay, so let's get to a case study here, an example problem, just predicting winter weather precipitation type. I won't go into too much of the diagram here, but essentially, on the left here, we just have a vertical profile. This is a skew T diagram, but it's really, just think of our model as a columnar-based model, essentially. We're just taking a single column of a vertical slice of the atmosphere. We're saying, what's the temperature up through time? What's the dew point? Maybe what are the winds? We're using that as our input. And then we're trying to say, okay, mapping that to a frozen precipitation type. We're using the model. All that matters is it's giving an uncertainty value and a probability of a certain frozen precipitation type. I won't talk too much about the data here, but there's tons of data challenges. I already mentioned it for this particular project. I selected this for the demo essentially because we're using crowdsourced data here. So you can imagine the biases in crowdsourced data. But the reality is we don't have good observations of precipitation type like over wide periods of time. Like there's very few observation locations. Some of them don't have all the types that we're interested in, et cetera. But there's a lot of different problems in crowdsourced data, of course. There could be false reporting, bad timing, inconsistent reporting, et cetera. And then here's a diagram just kind of showing, if you look at the blue distribution, essentially, you don't have to be a meteorologist to understand that like snow, they were seeing a bunch of observations when it's like 20 degrees C outside, not physical, at all, right? This is on a log scale, but still there's hundreds, if not sometimes thousands of unphysical observations across all the different types, right? Freezing cold weather where you're getting regular rain, and frozen types in summer weather, right? It turns out that after examination, some of this was because people were reporting ice pellets, also known as sleet, as hail in the middle of the summer. So they just didn't know the difference, and there was no training provided for that. Another hypothesis is that sleet is often, in Europe, is thought of a mix of rain and snow, actually, which is actually an incorrect definition. So here's just some composite analysis, right? On the left here, I won't go into any of the detail other than to say that that red line for sleet and ice pellets is totally physically impossible. Like that is not realistic, right? And over 50% of the data essentially accounted for that, right? So we had to trim almost 50% of the data away to get a physically consistent result for this. And I think this could be applied to all sorts of different data sets. Okay, let's talk about some actual XAI methods or XAI algorithms. Some simple ones, just for example. Here's a partial dependence plot. I'll start from left to right here because there's a lot going on here. But a partial dependence plot is essentially, let's take one feature, let's perturb it through some defined space or something, and then let's just, as we define it or as we perturb it, let's take the mean prediction of the rest of some subset of the data set, and plot that points and perturb it all the way through. You can imagine how correlated features is a major problem for this, right? Because we're not perturbing all the other ones. So on the left, you get these curves as to how sensitive when we're just kind of mapping that against surface temperature there. Yeah, maybe the curves have the right kind of like gradient or like slope direction, right? Positive versus negative, but the curves are not convincing from a probability standpoint. If you're finding a mean probability of rain at, freezing cold temperatures of still at 0.6, for example. That's just not physical, right? So one potential solution in the middle is, what if we perturb in a meaningful way more than one variable at a time, right? And so we just took like 5 or 6 different, layers of the atmosphere, vertical stacks, right? And we perturbed them at the same time. But we also, instead of perturbing them all along the same values, we actually perturb them with respect to their own distributions, right? So it actually preserves some curvature in the actual vertical profile to maintain some physicality. It's not perfect, but it's a lot better. Our curves look much more realistic. And the last thing on the right I really want to highlight is that it seems like all XAI essentially oftentimes it's just kind of being applied to probabilities or whatever the raw kind of like categorical variable or probabilities, right? But models now have all sorts of different ways to kind of calculate uncertainty and other metrics coming out of the model. Well, any of that can be looked at through the lens of AI or XAI, right? It doesn't just have to be the probabilities. So in this example, we're literally looking at the uncertainty rather than the probabilities in the middle, uncertainties on the right. And you see like a very good physical relationship there. Like I won't go into detail, but like the peaks of like where we expect that to be uncertain, and we do expect uncertainty because there's a lot of overlap and we don't have good resolution in our models. But where we see the uncertainty spikes in that particular diagram is exactly where we would expect to see them, which is awesome. Okay, another, here's some work from an intern of ours that did some, input times gradients, if you're familiar with this XAI method. But this is just kind of getting creative again, right? This is not just applying some XAI to our entire data set and plotting one bar graph, saying that like, here's the most important features, right? Like, let's look at some case studies and some regime-based analysis to see what happens, right? And this is just an example of, again, sleet or ice pellets. And it's just an animation showing that what's the most important height, in the atmosphere of the feature as it kind of moves through time, right? And so this is showing like right before the cold front where we're seeing ice pellets, it's actually the most important feature is actually sinking, going down closer to the surface where we'd expect a warm layer and then a sub-freezing layer again. So just a good example of like, okay, physically this is making some sense. Okay, now I want to talk about some interactive stuff that I'm really excited about. Here's just a JavaScript tool to visualize some of this precipitation type data. The first part here is nothing super novel, but we can kind of animate through time. You can kind of hover over and kind of see specific probabilities and uncertainties. You get to click on a specific point and see the vertical sounding on the right. But I'm going to pause it and kind of just like go through like, this is like part that I'm probably most excited about of this is that now we've dynamically linked the ML inference stage to the actual interactive plotting. And so as you'll see, now we'll let the user actually toggle and kind of play around with the sounding and move it however they want. And that's dynamically linked to our ML model and the inference stage itself. And then showing beneath that the actual statistics and the probabilities and the uncertainty that's actually showing. So this is where I think we could potentially go. You'll see us kind of modify this sounding now. This has nothing to do with the real data. You can take this out of distribution. You can do whatever you want. And so a forecaster, for example, could just say, okay, well, what if I do this? Let me make a sounding that I think would be this specific precipitation type. Does that match my intuitive belief or not? You can give it something crazy way out of distribution and see how the model reacts. Does it have a good failure mode or not? And then of course you can kind of overlay any other meteorological features. Okay, next I'll just go one other quick. Okay, hopefully. Sorry about the delay there. All right, and so what is this platform? I'm just going to briefly go over this. This platform credit is essentially, it's an open foundational platform for developing and deploying AI and full AI-driven weather systems. We've also got one for climate as well. And essentially, I think this is a really good platform to potentially investigate some of these physical AI systems. So we've got pre-trained model, you can train your own, et cetera. So demonstrating some of a really cool tool that I really just found out about yesterday, essentially, is, or I guess earlier this week, this Napari tool. I'm not sure if anyone was at the tutorial yesterday, but it was great. And so this is a tool directly through Python to be able to visualize some of this data, right? And so I'm going to show you some of this full AI kind of output, essentially. All this was a 4-dimensional NumPy array that I just loaded up in 3 lines of code. And I'm literally straight from Jupyter Notebook, and now I'm just kind of iterating through time here, rendering this all dynamically. This is just long lat grid. It's showing 9 different variables at a time. We're kind of seeing how, I won't go through all the variables, right? But we see different winds. You see the solar radiation kind of feel to the top right. On the top left is kind of this perturbation where I kind of added a baroclinic instability to see if it actually produces a physically based baroclinic wave, and it kind of does in this particular case. So just an unbelievably amazing tool that our community, and I learned this from the bioimage community, right? Like nobody in our community is actually using this, right? And it's such a powerful tool. Here's another example coming up of seeing some stuff. I'm gonna skip ahead a little bit, showing some stuff in 3 dimensions. You can look at, if we skip ahead to, you can do the same thing in 3D and iterate in time just as fast. It renders. You can look at different jet streams if you want and kind of render through this. This is like 4 lines of code in Jupyter to load this up and look at this. You can really inspect physical systems, from this that might take dozens and God knows how long, much time in Matplotlib to kind of get through some of this stuff. And then lastly, I'll kind of demonstrate that you can also do it over topography and some other things to see if it kind of physically is respecting some of that those bounds. So I'm a little bit short on time, so I'll kind of skip ahead. So what are the takeaways? So our takeaways, they might not be, the traditional methods might not be very well suited for system science, but we can, certainly be creative and modify them to obey physicality. We can apply them to other forms of output, such as uncertainty, which might relate to physical situations. We need to be very careful about our interpretation of XAI, as most methods don't even consider feature interaction, right? And how can we include that in our analysis? The interactive analysis can be a much faster and informative way to interrogate data. This is the one I'm most excited about. The integration of ML inference and interactive analysis simultaneously can be an incredibly powerful way to discover relationships and inspect failure modes and physical understandings. And then feature engineering, of course, can help increase explainability as well. So that's pretty much what I have. I just want to say that there's so many awesome tools I learned about just in the last couple of days here. A lot of awesome work in this. This is a call if there's our system scientists. If you have ideas as to how you want, explainability, in your models, or how you want to interrogate your data to get more physical explainability, please speak up and let the developers know. I mean, that's, I think, the beauty of this conference. So with that, I'm happy to take questions. Thanks so much.
For a wonderful talk, Charlie. Are there any questions? Great, we'll start here, and I'll give you the mic, and if you could just introduce yourself.
Sure. My name is Nick McCarty, and I am a consultant. I focus on data visualization and other things. I have a question about the JavaScript tool that you built.
Sure.
Did you use D3 to do that, or what did you?
That was built on React, I believe D3 as well. I didn't specifically build that one particularly,
okay.
but I can talk a little bit more.
That's real cool.
Afterwards. Yeah.
Thanks.
Yep.
Also, Nick, was it? Yeah. I like your GPU poor baseball cap. Yeah, I feel like I've climbed the social ladder to be GPU middle class these days, but yeah, getting there. Hey, if you could introduce yourself.
I'm Shubhoshit Ray, and I'm a postdoctoral fellow for Florida Atlantic University, where I do healthcare research, and interpretability is a main factor in there. So I have been using libraries called SHAP, Lime, and other things. One thing that you mentioned in your talk is like physicality of things, and I can come across like physics-informed deep learning.
Sure.
And things like other methods like group theory representations and things like that. But I haven't come across libraries that tackles the questions from a physics standpoint of view. Like, if you have this, you cannot have this, because under the physics setup, the energy cannot be defined like that. So what is the alternatives instead of building like physics informed or some biology informed or some dynamical systems informed architecture into your deep learning? Do you have any other simpler, like for who are not like domain experts but data scientists, to tackle that problem, or is there anything that is being under development? Thank you.
Sure, great question. I wish I had a simple answer for you. I don't think so. I think that it's too domain specific to be able to do it, which is why I think I really highlighted some of the domain specific kind of perturbations and everything. And as a community, each specific community, I think, can really talk about, like, if they come up with creative kind of regimes and ways to perturbate things, then I think that we can come up with some software to actually then kind of get some more kind of built out packages for XAI that will work for specific things. But to do that across different scientific disciplines seems rather ambitious and challenging to me. I'm not totally convinced it could be done. But like you say, physics-based neural networks and some of the other kind of constraints and these hybrid models of doing that might also be a satisfactory solution. It might not necessarily show you the exact kind of attribution or equations, but it could be a step in that direction, I think. But that's something too that I don't know if all models are going to, in the Earth systems are going to, move to this hybrid approach. The only other thing I'm thinking of is maybe like symbolic regression or something, but that's extremely expensive for big deep learning models, and I don't think that that's necessarily going to work. But you might be able to derive some physical equations from some simpler models.